Imagine a place in the universe where time slows down, light vanishes, and the very fabric of reality unravels. A realm so extreme, it defies everything we know about physics, a place from which not even light can escape. This isn't science fiction. It's the real, terrifying, and awe-inspiring frontier of space, the black hole. A gravitational monster cloaked in mystery and darkness, a black hole is not just a cosmic anomaly, it's the edge of known physics. For centuries, black holes have existed only as mathematical whispers, theoretical shadows, and Einstein's equations. But today they stand as some of the most mind-bending and captivating phenomena in the entire cosmos. This is the story of how we first found them, what we now know, and how these invisible giants are reshaping our understanding of space, time, and the very essence of existence. It all begins with Albert Einstein. In 1916, while formulating his revolutionary theory of general relativity, Einstein predicted the possibility of black holes, objects so dense that they would warp spacetime around them into a point of no return. At the time, the concept seemed too outrageous, a bizarre consequence of mathematics rather than a description of physical reality. For decades, black holes remained an intellectual curiosity, dismissed by many as theoretical absurdities. But space, as it turns out, had other plans. The universe began whispering its secrets to us, and slowly, those whispers turned into undeniable evidence. That moment of cosmic revelation came in the 1960s, when astronomers studying the Cygnus star cluster noticed something peculiar. A luminous blue star was behaving oddly. It was orbiting something invisible, something massive, yet it emitted no light, no signal, no form. It was as if the star was dancing with a ghost. But this wasn't a ghost. It was a gravitational predator. Further analysis revealed that the companion was pulling material from the blue star, heating it up and unleashing torrents of X-rays into space. This celestial vampire was named Cygnus X-1, and it became the first strong candidate for a real black hole. For the first time in human history, we weren't just imagining black holes. We were looking at one. Cygnus X-1, located about 6,000 light-years from Earth, is a stellar mass black hole. It formed from the remnants of a giant star that collapsed under its own gravity, compressing its core into a point of infinite density. The gravity around it is so powerful that even light, traveling at the fastest speed in the universe, can't escape. That's why it appears black. Not because it is empty, but because it is a place from which nothing returns. Over time, discoveries like this began to pile up. Astronomers started finding more black hole candidates, hidden in binary star systems, in the hearts of galaxies, and in the quiet corners of space. Some were a few times the mass of our sun. Others, monsters known as supermassive black holes, were millions or even billions of solar masses, residing at the centers of galaxies like monstrous gravitational engines. And suddenly black holes were no longer rare. Scientists now believe that there could be over 100 million black holes lurking in the Milky Way alone. What's even more astonishing is how these invisible objects shape the cosmos around them. Their gravitational pull can dictate the motion of stars, trigger galactic evolution, and unleash jets of energy that travel across interstellar space. But perhaps their most terrifying power is what happens when something gets too close. As an object falls toward a black hole, it crosses an invisible line called the event horizon. This is the point of no return. Once crossed, escape is impossible. Nothing, no spacecraft, no signal, no light, can make it back. And for anything unlucky enough to drift close, the process is gruesome. It's called spaghettification. A rather silly name for a deadly serious process. As you approach a black hole, the difference in gravitational pull between your head and your feet becomes so extreme that your body would be stretched into a long, thin filament, like a strand of spaghetti. Molecules are torn apart. Atoms are disassembled. You become a stream of matter, stretched and twisted, as you're pulled toward the singularity, the heart of the black hole, where all known laws of physics collapse. It's not just the end of matter. It's the end of understanding. At the singularity, density becomes infinite, time ceases to function in any way we understand, and space folds in on itself. In this place, human knowledge hits a wall. And yet, we keep searching. Despite their danger and mystery, black holes have become cosmic laboratories for exploring the boundaries of science. In 2021, humanity achieved one of its most astonishing feats, the first direct image of a black hole. Using a planet-spanning network of telescopes known as the Event Horizon Telescope, scientists captured a photograph of the black hole at the center of the M87 galaxy, over 50 million light-years away. The image wasn't just a blurry ring of fire, it was a revelation. It showed that black holes aren't just theoretical oddities. They are real, they are active, and they are more complex than we imagined. The image revealed 3 key layers that make up the anatomy of a black hole. First is the event horizon, the outer boundary, the limit of escape. Cross it and you're gone. No signal, no light, no hope. Next is the photon sphere, a mysterious region where light itself orbits the black hole endlessly. Imagine photons, those tiny packets of light, trapped in eternal loops by gravity. They neither fall in nor escape. They simply circle forever. And finally, deep within, is the singularity. The point where spacetime curves into a knot and the equations of general relativity break down. It's a realm where our current understanding of physics simply doesn't work. Quantum theory, gravity, time, energy, all of it becomes meaningless in the face of the singularity. What happens there? No one knows. And that's what makes black holes so endlessly fascinating. Every black hole shares this 3-layer structure, but they're not identical. Each one behaves a little differently, shaped by its mass, spin, environment, and history. Some feed quietly, slowly consuming matter. Others are voracious, devouring stars and emitting colossal jets of energy. Some rotate, twisting spacetime into whirlpools. Others remain still, lurking silently. And because we can't visit them, because any probe we send would be torn apart, scientists have had to get creative. Black holes are studied through indirect observation. We watch how stars move around them, how gas heats up and glows as it falls inward, how X-rays are emitted as matter spirals down the gravitational drain. Every flicker of light, every gravitational wave is a clue. A cosmic breadcrumb leading us deeper into the mystery. And in that darkness, we found some astonishing truths. Take M87 for instance. The black hole captured in that historic image is a supermassive beast. It weighs more than 6 billion suns. Yet it fits within a space smaller than our solar system. Its gravitational influence spans light years. It shapes the galaxy around it, pulling in stars, affecting orbits, and fueling massive energy bursts. It's a black hole not just of mass, but of power. A force capable of altering the destiny of entire star systems. The more we look, the more we realize that black holes aren't just cosmic oddities. They're foundational to the universe. They form during stellar deaths, reside at galactic centers, and might even play a role in how galaxies evolve. Some theories even suggest that black holes could be connected to other universes through theoretical constructs known as wormholes. Others posit that black holes could contain the seeds of new universes, each singularity a Big Bang in disguise. It sounds like science fiction. And maybe it is. But every time we peel back a layer of mystery, we get closer to turning fiction into science. Yet for all we've learned, the truth is humbling. Black holes remain in many ways beyond our grasp. They are nature's most perfect mystery. A place where knowledge bends, light ends, and reality warps into something unrecognizable. But that's exactly why we keep looking. Because in their darkness, we see the light of discovery. Because in their silence, we hear the call to understand. And so, we keep watching the stars. We keep chasing the shadows. Because somewhere out there, in the cold black heart of the universe, the truth is waiting. In 1963, a seismic shift in astrophysics occurred when Roy Kerr unveiled a revolutionary solution to Einstein's field equations. One that described not just any black hole, but a rotating one. Until that point, black holes were considered simple, featureless objects defined only by mass and, occasionally, charge. But Kerr's insight cracked open a hidden dimension of complexity. His model introduced the idea that black holes could spin, and in doing so, he changed the way physicists would think about the cosmos forever. Central to this rotating black hole solution was a bizarre and deeply intriguing region known as the ergosphere, a toroidal space surrounding the event horizon where the rules of physics appear to bend. Here, spacetime is dragged around by the black hole's rotation, creating a region where escape from the black hole's pull is technically possible, but motion in the opposite direction becomes impossible. It's a liminal zone, neither fully free nor entirely trapped, defying easy categorization and inviting both awe and confusion. The ergosphere wasn't just an oddity, it was a doorway to something even more fantastic. Within Kerr's mathematics, buried among the swirling chaos of spinning spacetime, lay a hidden implication: the theoretical existence of a tunnel-like structure now known as an Einstein-Rosen bridge, or more popularly, a wormhole. These hypothetical tunnels through spacetime, first hinted at by Einstein and Rosen decades earlier, were suddenly back in the spotlight with new relevance. Kerr's black hole offered not just destruction, but the remote possibility of connection, a bridge between distant corners of the universe, or perhaps between entirely different universes altogether. Though wildly speculative, The idea captured imaginations across physics, philosophy, and science fiction alike. To understand why wormholes ignite such fascination, we must revisit the very foundation of modern physics, Einstein's general theory of relativity. In this framework, space and time are not separate, rigid arenas where events unfold. They are part of a four-dimensional fabric, space-time, that bends and stretches in response to mass and energy. Massive objects like stars or black holes create dimples in this fabric, curving space-time around them and guiding the motion of anything nearby. Wormholes, then, are conceptualized as extreme deformations of this fabric, shortcuts or tunnels that bypass the traditional paths through space. A journey that might take tens of thousands of years traveling at the speed of light could, in theory, be reduced to mere moments through a stable wormhole. It is the closest thing to science's version of magic. But the physics of wormholes is treacherous. Their stability, if they even exist, is fragile. Theoretical analyses suggest that they would collapse instantly unless propped open by something utterly alien to our current understanding: exotic matter. This isn't just strange matter. It's hypothetical material with negative energy density, capable of counteracting the tremendous inward pull of gravity. Such a substance has never been observed in nature, though some quantum effects hint it might not be impossible. Add to this the wild instability caused by quantum fluctuations and high-energy radiation near a wormhole's throat, and the whole concept begins to unravel at the edges. Still, the hope remains. Because if wormholes could be stabilized, they wouldn't just enable fast travel across the cosmos. They might unlock time travel itself. The implications for humanity are staggering. These theoretical gateways represent not just a transportation revolution but a philosophical upheaval. They suggest that the universe may be far more connected, dynamic, and bizarre than our current observations suggest. As scientists peer deeper into these theoretical constructs, they're driven by more than just curiosity. They seek unification, a single framework that ties together every force and particle in the universe. This ultimate theory, often referred to as a theory of everything, would reconcile the four fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into one coherent model. One of the most compelling candidates for this grand theory is known as superstring theory. Unlike traditional physics, which models particles as tiny points with no size, string theory proposes that every fundamental particle is actually a minuscule one-dimensional string, vibrating in specific patterns. Each mode of vibration corresponds to a different particle, just as different notes emerge from the vibration of a violin string. It is an elegant vision of the cosmos, where the universe itself becomes a symphony and physics its melody. But string theory doesn't just reimagine particles. It demands an entirely new conception of reality. For the mathematics to work, the theory requires additional spatial dimensions, far beyond the familiar three. In most string theory models, the universe operates in 10 or even 11 dimensions. These extra dimensions aren't obvious because they're thought to be compactified, curled up so tightly that they elude direct detection. To visualize this, imagine a tightrope stretched across a canyon. From a distance, it appears one-dimensional. But to an ant crawling along it, the rope's cylindrical surface reveals another direction to move, one invisible at larger scales. Similarly, humans may exist in a world with unseen dimensions surrounding us, shaping the laws of nature without our awareness. These compactified dimensions are more than theoretical curiosities, they're essential to how the universe behaves. The exact shape and topology of these hidden realms may determine the masses of particles, the strengths of forces, even the very constants of nature. In this view, physics isn't just about observing nature, it's about discovering the deep geometry behind it. And yet, for all its beauty and potential, superstring theory has a frustrating flaw. It is almost entirely untestable with today's tools. The energy scales at which string effects become apparent are far beyond the capabilities of even our most advanced particle accelerators. Still, the theory's mathematical power has made it an indispensable tool in modern physics. It has inspired new insights into black hole thermodynamics, quantum gravity, and the fabric of spacetime itself. It is here, at the intersection of black holes, quantum mechanics, and string theory, that we encounter one of the most perplexing mysteries in all of science: the quantum black hole. These are not the classical giants that warp galaxies, but tiny, theoretical objects where the smooth curves of general relativity collide with the probabilistic chaos of quantum theory. In this realm, the rules begin to break down. Paradoxes emerge. One of the most famous is the information paradox. The troubling idea that information falling into a black hole could be permanently lost when the black hole evaporates. This would violate a sacred tenet of quantum mechanics, that information is never destroyed. For decades, this conundrum has baffled physicists and spurred some of the most intense debates in the field. And yet, slowly, tantalizing pieces of the puzzle have begun to emerge. Researchers have found that in simplified two-dimensional models, versions of string theory might actually resolve the information paradox, preserving information in subtle, non-obvious ways. These models are not direct reflections of our universe, but they hint at a deeper consistency within the theory. If such mechanisms hold up in more realistic models, they could pave the way toward understanding the true quantum nature of black holes. Edward Witten, one of the most influential string theorists alive, once described string theory as 21st century physics that fell by accident into the 20th century. The quote captures the sense of awe and frustration that surrounds the field. It feels like a glimpse into a deeper reality we're only beginning to comprehend. The unification of general relativity and quantum field theory remains the holy grail of theoretical physics. These are our two most successful frameworks, one describing the grand architecture of the cosmos, the other governing the subatomic realm with uncanny precision. And yet, they remain incompatible at the deepest levels. A truly unified theory would not only describe the universe but explain its origin, its fate, and the strange phenomena that dwell at its outermost frontiers. That search continues, driven by the belief that somewhere within the chaos of equations lies a deeper truth waiting to be uncovered. Black holes are not just astronomical oddities, they are the crucibles in which our understanding of space, time, and matter is tested to the breaking point. They force us to confront questions that blur the lines between science and philosophy. What happens at the edge of time? Can causality survive in a universe that allows for wormholes? Does reality have a fundamental shape? The more we study black holes, the more we realize they are not cosmic endpoints, they are beginnings. Portals to new physics. Gateways to the unknown. And perhaps, one day, the key to unlocking the ultimate secrets of the universe.